Dear students, let us now see the engineering stress strain and true stress strain. Engineering, that is, it is also known as the nominal or conventional stress strain. Okay, now see, so whenever in the tension test, this is our specimen with the original cross-sectional area AO, it is subjected to the tensile loading. P is the tensile load applied on this specimen. So here, when in the calculation of the stress, sigma n is the nominal stress, we are using the applied load divided by the original cross-sectional area, then that stress is known as the nominal or engineering stress. Okay, so whenever we are assuming that, even though of course there will be the change in the area as we are applying the tension load, definitely the length is going to increase and the area is undergoing the reduction. And finally, if you talk about this mild steel stress and strain graph, so there will be the failure after the cup and cone shape failure. So here, this nominal stress is calculated with respect to the original cross-sectional area. Okay, we are assuming that the cross-sectional area remains same throughout the tension test. Okay, so this is the nominal stress, and when you talk about the strain, it is represented by this engineering strain, small e. Okay, so what is this strain? So because of this load, when the specimen is undergoing the deformation, so change in length, so this is the original length of the specimen, L original, and after application of load, say change in length, the specimen is now reached to the length LF. So here the strain in this specimen is nothing but the change in length because of the loading divided by original length of this specimen. So what is change in length? Change in length will be what? The final length minus original length, LF minus LO divided by LO, that is original length. I can write is delta L divided by LO, or I can write this DL upon LO is my engineering strain or nominal strain, where sigma n is my nominal stress, isn't it? So see, this is our stress and strain, which is the engineering stress and strain. Now, if we want to see the true stress and strain, so what is the difference in that actually? Now I am talking about the true stress and strain. After that we are going to see true, this is also known as, that is, it is natural or logarithmic stress and strain. So here, while calculation of the stress, we are taking the instantaneous area for the calculation of the stress. So when, if I say I want to define the true stress, so it is equal to the applied load, and because of this load, the specimen is undergoing change in its length. of course the area is going to decrease and length is going to increase. So whatever the instantaneous, because it is the instant to instant measured stress or measured strain, isn't it? So applied load divided by the area at the time of measurement, or I can write here instantaneous और फाइनल, जो भी आप जहां पे मेजर कर रहे हो, दैट इंस्टेंटेनियस एरिया इज taken for the calculation. So AI P divided by A or P divided by AF, I will write this instantaneous area like this. Okay, so this is the true stress. This is the true stress. If with the stress strain curve, so this is the true stress versus this true strain epsilon. Okay, so this is the sigma t true stress and this is the true strain. So basically if you look at this stress strain curve for this engineering stress strain and this true stress strain curve, so definitely the true stress strain curve will go like this. Okay, because there is continuous decrease in area. Okay, so see here we have got here the true stress. Now the true strain in this is represented by epsilon, is our true strain. It is our true strain. And what is the value of this true strain? So it is nothing but the summation of all the nominal strains instant to instant. Okay, suppose if I want to have the strain epsilon f, I want to calculate say the strain at the time of fracture or failure. So here the strain can be calculated by whenever in the measurement whatever the values I am having for the engineering strain. So okay, say suppose this is E1, E2, E3, E4 up to E5, isn't it? So the true strain is nothing but of summation of all the nominal strains instant to instant. Say for example E1 will be what? The L1 minus L original divided by L original. E2 will be what? L2 minus L1 divided by L1. Like that, whatever the values of the engineering strains, so up to the point where you want to measure that true strain, it is a summation of all that nominal or engineering strains. So here what I can write? It is nothing but summation of what? E1 plus E2 plus E3 up to यहाँ पे E5 तक है, okay, plus up to E5. So I can write like this, because it is what? E is nothing but what? Change in length divided by original length. So everywhere there is a change in length divided by original length, but it is a summation, so I can write dl upon L, isn't it? And when I want this true strain, so it is nothing but the summation of all the strains, so I can write in the form of integration, that is epsilon is equal to ln of, epsilon is equal to integral कहाँ से कहाँ length L original to L final, L original to L final dl upon L, isn't it? So I get the value for true strain. So if I integrate this, that is epsilon is equal to this, that is 1 upon L dl, it is ln of L and limits from L original to L final. What I can get for true strain is equal to ln of L final divided by L original. Very important, this is the value or formula for the true strain. Okay, whereas true stress is what? It is dl upon L, and true strain it is natural log of L final divided by L original. Now for this specimen, suppose if, of course in metal forming we are saying that the volume constancy principle is valid. So if it is true, then I can write for the specimen the volume before deformation, that is A naught into L naught, should be equal to volume after deformation, that is A final into L final, isn't it? So for here, what I can write for this LF by LO, that is L final divided by LO, I can write it as A original divided by A final. Very important. If I put this value here, then I can write the true strain like this also. True strain is equal to ln of A original divided by A final. And if this cross section is circular, then again we can simplify further, that is ln of, this is pi by 4 d original square divided by pi by 4 d final square. So pi by 4 get cancels, so epsilon is equal to 2 ln of, I can write d original divided by d final. So this is also the format or formula for the true strain. Okay, now see here, in the metal forming कौन सा स्ट्रेस अपने को ज्यादा रियलिटी की तरफ ले जाता है? So which stress is more consistent in the physical phenomena, that we have to see, because both the strains are there, engineering is there and true is there. So let us take an example. Suppose, see here, I am having the rod of length L original, okay, and this rod of length L original I am going to deform with this, say, tensile load P to the double of this value. Okay, so L final which is 2 times of L original. Of course tensile loading is there. So in this case, this is case number 1 I am taking, say this is case number 1, and case number 2, the same rod or same specimen I am going to compress to the half of its original length. So this is the L original. So after applying this compressive load, okay, it is going to be the, say, half of it. Okay, so it will be L original upon 2. And please keep it in mind that I am considering the strain, that is for tension it is positive and compression it is negative. Let us see. In this situation, case number 1 and case number 2, let us try to calculate the nominal stress. Our engineering strain we will calculate. So what is E here? That is change in length divided by original length. What is your change in length? Original, that is final length, was 2x L naught minus original length L naught divided by original length L naught. So what is there? That is L naught divided by L naught. You will get the strain as a 1, isn't it? Now here the final length was L original by 2 and original length is L original. So what is E here? Change in length, that is LO by 2 minus LO divided by LO. That is LO minus 2LO divided by 2LO, that is minus 0.5, isn't it? So minus because it is compressive and plus because it is a tension. Now see here, for the small values of the strain, see यहाँ पे कितना आया? The strain is 1. In compression the strain is minus of 0.5. Okay, now if I want to have here the true value of strain, okay, the true value of strain is what? So epsilon is equal to what? ln of L final divided by L original. So what is of ln of L final kitni hai? Twice of L original divided by L original. So how much it is? ln of 2, that is 0.69 something, isn't it? You check it. And here if I want to calculate the true strain, how much it is? Ln of L final was what? LO by 2 divided by LO, that is ln of 0.5. How much it is? So hope it is negative 0.69. ln of 0.5. It is negative of 0.693. Negative of 0.693. Now see here. This is the value of true. This is the value of nominal or engineering strain. This is also the engineering strain, and this value of the true strain. This is the true strain. Of course, positive tension for compression, the value of strain will be negative. So very simple. Now see here, for the minimum values of strains, whenever we are dealing with the minimum values of strains, minimum working, so almost we can see here the value of the engineering strain and the value of the true strain are nearly equal, nearly same. You can see here, it was 0.5 engineering and true was minus 0.693. So these are quite close to each other. So no big deal. But whenever I am dealing with the large amount of deformation, whenever I am dealing with the huge amount of deformation, say for example, I'll take example. If the initial length of the bar or specimen, say L is 10 mm or height of the specimen was 10 mm, and I'm going to deform it, that is original was 10 mm and I want to deform it to the 0 height. See, 10 mm height hai initial, now I'm going to reduce it to 0 height. Say for example, now let us calculate the value of the engineering and true strain for this. Let us calculate. क्या मिलता है देखो आपको. So one thing is very much clear, dear students, that when the values of strains are very less or small, so there is no huge difference between the engineering strain and normal and our true strain. But let us see this example. In this case, I will first calculate the engineering strain. What is the formula? Final length minus original length divided by original length. So what is that? Final length was 0 minus original length 10 divided by original length 10. So of course, because it's compression, I am going to reduce it to 0. So negative 1 is my strain. But is this correct? Is this correct? I am deforming the specimen directly from certain height to no height. Tremendous deformation I am having in this material. Huge amount of working I have done on that material, then it comes to the 0 height. So let us see how much strain should be get induced in the material. Of course it should be infinite. The huge amount of strain should be get induced. But the true strain is, sorry, our engineering strain is just showing that the strain of 1, negative 1. But in actual, physically, if you seeing that, of course the huge amount of strain, let us see how much it is. True strain is equal to ln of L final divided by L original. Ln of final item is what? 0 divided by 10. And of course, if you see ln of 0, it is infinite and negative because compressive. So infinite strain should be there into the material. But see, this is the real picture of the process. Real picture we are seeing here. 10 mm का direct 0 height में मैंने deform कर दिया. I got the infinite deformation. This is consistent to the physical phenomenon. Okay, I am reaching towards the reality by taking the true strain. But you see, the engineering strain is showing me only negative 1. So that is the difference. At smaller values of strains, you can take the true or engineering, but whenever, because see, metal forming में ही क्यों लेना है true because we are going to have the tremendous deformation. We are going to apply the force, tremendous force. We are going to utilize the tremendous power for the deforming of the materials to have that deformation, isn't it? And of course, and we really want, or we want to reach towards the reality, then we have to follow this true strain, not the engineering strain, dear students. Please remember this. Okay, so that is the difference. We have to keep it in mind for this true strain and engineering strain. Now we will see what is the relationship between this engineering and true stress and strain. We are going to see the relationship between engineering and true stress and strain. Okay, very important. So we know that what is sigma T, that is a true stress, is equal to what? The applied load divided by instantaneous or final area. Here I am definitely going to take the instantaneous or final. I am not interested in the original. Now see, first of all we are going to see for the stress, and then we will see the relation between the strains, engineering and true. If I multiplied and divided by A original, what will happen? Nothing will happen, but I can write like this: P divided by A naught into A original by A final. We know that what is this P by A naught? This is our nominal stress, isn't it? And what is this A original by A final? For the volume constancy I have written A original into L original is equal to A final into L final. What is that? That is A original by A final, it is equal to L final divided by L original. We have seen this. So instead of this, I can write L final divided by L original. Now, from this, suppose if I subtract one and add one, what will happen? Nothing will happen. But I can able to write the sigma n into L final minus L original divided by L original plus 1. What is this change in length divided by original length? It is nothing but our engineering strain E plus 1. This is our sigma T, very important. So we get the relation between the true stress and nominal stress. That is, true stress is equal to nominal stress into bracket E plus 1, where E is what? Our engineering strain, that is delta L upon LO. Isn't it? Very simple. Now same fashion, we get the relation between the stresses. Now for the strains, very simple again, we know the strain is what? True strain, we know that it is ln of L final divided by L original. We have seen this formula. So again, same thing I am doing. I will subtract one, add one. What is there? So ln of L final minus L original divided by L original plus 1. So ln of, what is again this? Change in length by original length, E plus 1. Very, very important. Okay. So see, you get the relation between the sigma T and sigma N. Here you get the relation between the true strain and engineering strain. Okay. So please remember this many times. You will get the questions on these relationships. Dear students, now after seeing the relationship between this engineering and true stress strain, let us now have the strain rate. The strain rate. Okay. So that is the strain per unit of time is nothing but our rate of that strain. That is, again there we are having engineering strain rate, and there will be true strain rate, isn't it? So when I talk about this rate, I will write this E dot for engineering strain and epsilon dot for true strain rate. So what is this? D dt of this E, isn't it? And this is d dt of our epsilon. We'll get the rate. Very easy. So what is this? D dt of, you are having this strain, engineering strain, as this delta L divided by L original, isn't it? And if you see, this delta L is nothing but again this difference in the length is again going to get the length only, isn't it? So what I will do, I will take this 1 upon L naught, I will write here, into this d dt of L, isn't it? So here, what relation I am getting for this? The engineering strain rate small e dot is equal to 1 upon L naught, and what is change in length per minute time? That is nothing but the velocity of deformation, isn't it? The speed with which the jaws, where this specimen is held between these two jaws, how fast they are coming closer to each other, the speed, that speed is V. That is the velocity of deformation, divided by the original length, This is the formula for strain rate, engineering strain rate. Now in the same fashion, we can have the epsilon dot is equal to d dt of ln of what? LF by LO, isn't it? So that will be what? It is, what is the derivative of natural log of x? It is 1 by x, isn't it? And this L naught will be the, I will write like this, that is L naught, because it is divided by L naught, 1 upon LF, isn't it? I will write, this is dl by dt, I will write directly like this, into 1 upon LF, So I will get here, see, this again dl by dt is nothing but what? Change in length per unit time, that is velocity. That is velocity of deformation, divided by this LF is what? Final, or because it's a true, I can write final or instantaneous. The instantaneous or final length. This is the strain rate epsilon dot. And of course the unit will be what? It is per second. Or I can write the second inverse. This is the strain rate. Now dear students, if we look at this true stress and true strain curve, okay, of course this is sigma t and this is epsilon, and this is our true stress strain curve, isn't it? Now see, up to this yielding, okay, here in this stress strain curve, we are having the strain hardening region, okay, So this region is actually this region, and we are having this region, okay. So up to the yield point, okay, so up to the elastic limit, which law is valid here? So we know that up to the elastic limit, the Hooke's law is valid, isn't it? But here, as we are deforming the material and material is undergoing the strain hardening phenomena, it is getting harder and stronger, so we have to continuously supply the more amount of stress compared to the or maximum than the previous value, isn't it? We know that. So actually this strain hardening region is given with the flow curve equation, or this is the Holloman law. It is given with the Holloman law. That is, here the stress is proportional to strain here, isn't it? But here in the strain hardening region, this sigma T is equal to K times epsilon to the power n. This is the flow curve equation and it is got by the experiments. Okay. So where the sigma T we know it is the true stress, where this epsilon is the true strain. Okay, it is the true strain, corresponding true strain, and n is very important here. This K and n, these are new terms we got here. So what is this n? So n is our strain hardening exponent, hardening exponent or index, which will decide जितना ज्यादा strain hardening होगा उतना n की value क्या होगी, ज्यादा होगी. It is kind of the material property that we have. N is what? The material property, and the K is the strength coefficient, which is nothing but the value of the true stress for the true strain of unity. So when, see here, when the true strain is 1, so see here, so 1 to the power anything, it will be 1 only. So sigma T is equal to nothing but what? This K only, that is a true stress for the strain of unity. This is the strength coefficient. Okay, so what this flow curve equation tell us? That sigma T, that true stress, is equal to K into epsilon to the power n, where K is the strength coefficient, epsilon is true strain, and n is the strain hardening exponent, and which is very important, which will show you the presence of the strain hardening. So जितना मटेरियल ज्यादा strain hardening दिखाएगा उतना उसकी n की वैल्यू क्या होगी, ज्यादा होगी. It's a kind of material property. So of course when n is equal to 0, in this curve, suppose I can have the values for n like this. So this sigma T versus this epsilon. So see here, this I can have this or this value. See here, if this n is equal to 0, the slope is 0, n is equal to 0. This n is equal to 1. And this curve, for this curve, this n is greater than 0 and less than 1. So this material, when see n value is 0, these materials are, whenever the strain hardening exponent is 0, these material will be ideally rigid plastic materials. कौन से material होते हैं वो? Ideally rigid plastic material. For plastic materials, this n value, strain hardening exponent, is 0. Whereas the n is equal to 1. See here, n is equal to 1. Which is what? It is linearly elastic material. It is for linearly elastic material. And the third category range you can see here, the n value is from 0 to 1. But see, for most of the engineering materials, this value of strain hardening exponent lies between 0.1 to 0.5. Please remember, very important. So for most of the engineering materials or structural materials, rather I can say structural materials, the value of n is from 0.1 to 0.5. Okay, so this is very important, the strain hardening exponent. Now suppose if I plot this graph on log paper, so what I can get here, see, that is if I take the log of this, that is log of sigma t is equal to log of k plus n log of epsilon. I can write like this, log of sigma t is equal to n log of epsilon plus log k. So isn't it the same like the straight line, that is y is equal to mx plus c? Yes, that is, see here, the graph you will show like this. This is not the log curve, it will be like this. On log paper you will get this value like this, log of sigma t, and this is our slope n, this is the log of epsilon. And see, this intercept of this line on y-axis is nothing but our value of log k. See here, this is the intercept of the line on the y-axis, isn't it? So here definitely we can write that n is equal to what? Log of sigma t2 minus log of sigma t1. Okay, say at this point 1 and this is point 2, then definitely I can write divided by log of epsilon 2 minus log of epsilon 1, which is equal to log of sigma t2 by sigma t1 divided by log of epsilon 2 divided by epsilon. I can write the n like this also, isn't it? So please remember this flow curve equation or this true strain graph in the strain hardening region. This law is also known as the power law or the Holloman law. This is also known as the power law. क्या बोलते हैं इसको? Power law भी बोलते हैं, और it is a flow curve equation. And please keep it in mind that this sigma t, which is the true stress, is a function of here, is a function of the strain, comma true strain, comma temperature in Kelvin, and the microstructure of material. The microstructure of the material. Please remember this, very important.